The one-dimensional incline is an analysis of an object, a round object, rolling upward or downward on an incline. We are talking about the duration where the ball is rolling only on the hill, not after it rolls off the top or before it arrives off the flat horizontal surface. As such, the angle of the incline, theta, determines the acceleration of the object on the hill. We'll go into later that this is actually creating a fraction of gravity that is always directed vertically straight down in order to cause the object to decelerate on the way up or accelerate on the way down. That's simply what I want to talk to you right now about, is the idea that no matter what the angle, it is some value that is going to generate an acceleration on this incline that is down the hill. This acceleration is determined by the magnitude of the hill, and the direction is determined by the slope direction of the hill. And since the hill does not change angle or direction any time during the time that m is rolling or moving around on it, the acceleration never changes. The value, the magnitude never changes, and the acceleration direction never changes. To illustrate this, it's important to discuss what would occur to the ball in either direction at any point along the path. If we assume that V naught is directed up the hill when the ball begins, we can say that as the acceleration acts on the ball, later on in time, this ball will be moving slower up the hill. At some point, that velocity will decrease to a point where it stops for just a moment. In doing so, it does not stop moving permanently. It simply momentarily ceases its upward momentum and immediately begins to come back down. Why does it do that? It's round, it's on a hill, and there is an acceleration pulling it down the hill. That acceleration causes it to begin its motion back down the hill. In this case, it goes from a speed that is initially equal to 0, that then speeds up faster and faster until it returns to its original position, moving in exactly the opposite direction. This velocity is equal to the opposite of the initial velocity. This is true because the acceleration has not changed the entire time. As the ball rolls up the hill, the acceleration is down the hill, causing it to slow down. Once it's at the top, the ball starts at 0 and accelerates at a faster rate down the hill due to the fact that the acceleration is down the hill. The magnitude of the acceleration as well as the direction of the acceleration are both determined by the hill, and the hill does not change as the object moves around on it. Furthermore, you'll note that I made no reference to the mass of the object because, as you note in all your kinematics equations, the velocity, the acceleration, the displacement, and the time for the motion of an object is independent of its mass. So if this was a much larger object, much larger object, a boulder the size of a house, this exact same motion ideally will occur. It will start moving up the hill. It will decelerate down the hill due to the fact that it's on the hill. The hill does not change, so the acceleration is exactly the same for the purple object, a much larger object, as it is for a smaller object. As long as that object is round and rolls in a frictionless environment, this occurs.